Let's
I'm here and ready whenever you are. Just let me know what you need and we can dive right in.
let's understand differential equation.
Absolutely. Differential equations are a fascinating topic. We can start from the basics, like ordinary differential equations, ODEs, and then move on to partial differential equations, PDEs, if you'd like. Let me know which aspect you're most interested in or if you have any specific questions in mind.
Do I need to choose between two, or you can start with the early development intuition that lead to such a beautiful theory and help
Absolutely.
us to solve some of the nature and help us to understand. Okay, nature has already things happening, but the mathematical picture is captured by these differential equations.
Exactly. Differential equations really let us translate the dynamics of nature into a mathematical framework. They help us model everything from simple motion to complex phenomena in physics and beyond. We can definitely delve into the historical development and the intuition behind them as well. Just let me know how deep you'd like to go.
Okay, let's start. What are the early development and the intuition that lead to such a beautiful theory?
Sure, the development of differential equations goes way back to the 17th century. It all started with the work of pioneers like Isaac Newton and Gottfried Wilhelm Leibniz, who independently developed calculus. They were driven by the need to understand motion and change, like how planets move or how objects accelerate. The intuition behind them was basically about describing how a quantity changes with respect to another. For example, Newton's second law of motion, F equals ma, can be seen as a differential equation where force relates to the rate of change of momentum. Over time, mathematicians like Joseph Louis Lagrange and Pierre-Simon Laplace expanded these ideas, and the theory evolved to handle more complex systems. This laid the foundation for the rich and beautiful theory we have today.
Okay, how does that dynamics is being captured? What you mentioned about change with respect to another.
Great question. Essentially, differential equations capture dynamics by expressing how one quantity changes in relation to another, typically with respect to time or space. For example, if we look at Newton's second law, the acceleration of an object is the derivative of its velocity with respect to time, and velocity is the derivative of its position with respect to time. So we're essentially looking at rates of change. In a more general sense, a differential equation will relate a function to its derivatives. This means that if you know how the rate of change is, you can integrate that information to find the original function. This is how we model everything from simple harmonic motion to complex fluid dynamics. It's really about understanding how things evolve over time or space.
So, what was the real idea to build such a beautiful theory? One, you mentioned about the change. We observe change and we develop a method that help us to understand that change.
Exactly, you've got it. The core idea was really driven by the observation of how the world changes and evolves. Early scientists and mathematicians wanted a systematic way to quantify and predict these changes. By developing tools like calculus, they created a framework to describe rates of change and accumulations in a precise way. In essence, it was all about understanding and predicting natural phenomena, whether it's the orbit of planets, the flow of fluids, or the behavior of heat and waves. The beauty of differential equations lies in their ability to unify and model a vast range of phenomena under one mathematical umbrella.
So, whether orbit of planets or the fluid flow of fluids or behavior of heat or waves, the beauty of differential equation. So, first of all, they were working on those things. So, how let be more specific. Let's understand the orbit of planet that how this differential equations governs that.
Absolutely. Let's dive into that. When it comes to planetary orbits, the motion of a planet is governed by Newton's law of gravitation. Essentially, the gravitational force between the sun and a planet can be expressed as a function of the distance between them. This force leads to a second order differential equation that describes the planet's acceleration. In other words, the rate of change of velocity is determined by the gravitational force. By solving these differential equations, we can predict the planet's position and velocity at any given time. For example, in the case of a simple two-body problem, like the sun and a planet, the differential equations describe how the planet's position changes over time. When we solve these equations, we get orbital paths like ellipses, circles, or hyperbolas, depending on the energy and initial conditions. It's a beautiful example of how mathematics can perfectly describe physical reality.
So you are suggesting that the motion governed by the Newton's law of gravitation, forces between the sun and the planet can be expressed as a function of distance between them. So this force lead to the second order differential equation describes the planet's acceleration. In other words, rate of change of velocity is determined by the gravitational force. By solving this gravitational differential equation, we can predict the planet's position and velocity at a given time.
Exactly. And by doing so, we can not only predict the future position and velocity of the planet, but also understand the entire orbital path and the long-term behavior of the system. It's truly amazing how these mathematical frameworks can model the complexities of celestial mechanics so elegantly.
It's a long-term behavior of the system. It's truly amazing how this mathematical framework can model the complexity of. But okay. Uh, for describing and solving differential equation for the orbit of the planet, what are the things we required and how it develops and predict the dynamics? That is the elliptical orbit.
Great question. To describe and solve the differential equations for planetary orbits, we need a few key components. First, we need the initial conditions, like the initial position and velocity of the planet. Then we need the gravitational constant and the mass of the sun, which determine the strength of the gravitational force. Once we have these, we can set up the equations of motion for a planet in a central gravitational field. The equations typically reduce to a second order differential equation that relates the planet's radial distance and angular position. As we solve these equations, often using techniques like conservation of angular momentum and energy, we find that the solution naturally takes the form of an ellipse, as described by Kepler's laws. The elliptical orbit emerges because the gravitational force acts as a central force that keeps the planet in a stable path. In summary, it's this combination of initial condition, the gravitational parameters, and the mathematical framework of differential equations that lets us predict and understand these beautiful elliptical orbits.
But okay, but how does this specifically second order differential equation works for this case?
Great question. In the case of planetary orbits, the second order differential equation typically comes from Newton's second law applied to the gravitational force. For example, if we consider the radial motion of a planet, the gravitational force is proportional to the inverse square of the distance. When we write out the equation, we get something like the second derivative of the radial distance with respect to time equals the negative gravitational constant times the mass of the sun divided by the radial distance squared. This forms a second order differential equation because it involves the second derivative of the radial coordinate. By solving it, we can find the planet's radial distance as a function of time, and combined with the angular motion, we can describe the full elliptical orbit. It's this interplay between the radial and angular components that yields the beautiful elliptical pulse we observe.
Okay, first of all, what we can see that if there is a two body system, Earth and the Sun, there is a gravitational force acting between them, and they are separated by a distance r, might, and r is changing basically. That is the observation, and but how that observation map to the actual mathematical picture, that is a differential equation, and how that solves that dynamics.
Absolutely, that's a great point. In a two body system like the Earth and the Sun, the distance between them indeed changes over time as the planet orbits. To capture that mathematically, we set up differential equations that describe how the radial distance and the angular position evolve. In practical terms, we break the motion into two components, the radial component and the angular component. The gravitational force influences the radial acceleration, and the planet's angular momentum determines how it moves around the sun. By combining Newton's second law with the inverse square law of gravitation, we get a set of coupled differential equations. One equation describes how the radial distance changes with time, and the other describes how the angle changes. When we solve these equations, we see that the planet's orbit forms an ellipse, and the changing distance and angle are interconnected. In other words, the observed changes in distance and angle are directly mapped to these differential equations. And by solving them, we get a complete picture of the orbit. Is that mathematical translation of physical observations that allows us to predict and understand the dynamics of the system.
But how did that such a huge discovery led to the profound implication? I mean to say that okay, we observe that thing, but here we observe two parameter that dependence on angle and the radius, and then we see that both are changing. But how we encode such information in such a beautiful mathematical picture and solve and understand the context. What was the
That's a
initial idea that leads, forget about this two body system, but what was the initial idea that led to the development of this thing?
Absolutely. At the heart of it, the initial idea was really about understanding how nature changes and evolves. Early scientists and mathematicians like Newton and Leibniz were driven by the curiosity to describe the motion of objects in the universe. They wanted a systematic way to capture how quantities change over time and space. The beauty of differential equations emerged from the need to describe these dynamic systems in a precise, quantitative way. It started with simple observations like how falling objects accelerate or how planets move in their orbits, and then evolved into a robust mathematical framework. In essence, the initial spark was about creating tools to model the changing world, and from that, differential equations became a fundamental language of science and engineering. It's really that deep curiosity and the drive to understand the patterns of nature that laid the groundwork for everything that followed.
Okay, how basically the dynamics that we are observed and the changes that we see, how we capture that information mathematically.
Exactly. It's all about translating those observed patterns and changes into a mathematical language by identifying how quantities depend on each other, like how position changes with time or how force influences acceleration. We can use differential equations to capture and predict that behavior. It's really that blend of empirical observation and mathematical formalism that makes the theory so powerful and beautiful.
Tell me one idea that is very interesting to know about the differential equation according to you.
One really fascinating idea is how differential equations can describe not just physical phenomena, but also complex systems in biology, economics, and even social sciences. For instance, in ecology, differential equations can model population dynamics, showing how species grow, interact, and evolve over time. It's amazing how a single mathematical framework can be so versatile and reveal patterns across such diverse fields. It really highlights the universality and elegance of differential equations.
Okay, tell me one example from biology where we can see.
Absolutely. One classic example in biology is the logistic growth model, which uses a differential equation to describe how a population grows over time. Initially, the population grows exponentially, but as resources become limited, the growth rate slows down and eventually levels off. This leads to a sigmoid curve, and the differential equation captures that balance between the growth rate and the carrying capacity. It's a perfect example of how differential equations help us understand and predict biological phenomena.
What was that logistic growth model and a population grow over time? That was thing.
The logistic growth model is a way to describe how populations grow in an environment with limited resources. It starts off with exponential growth when the population is small and resources are abundant. But as the population increases, resources become scarcer and the growth rate slows down. Eventually, the population reaches a stable equilibrium called the carrying capacity, where the rate of growth is zero. The logistic equation captures this dynamic by balancing the growth rate with the limiting factors, giving us a realistic model of how populations behave over time.
So basically, sometimes solving this differential equation give exponential growth, exponential solutions, because sometimes nature behavior is like a exponential.
Exactly, you've got it. When resources are plentiful and there are no significant constraints, populations often follow exponential growth, and that's reflected in the solutions to the differential equations. But as we introduce limitations like carrying capacity, the growth slows and shifts to a logistic pattern. It's really fascinating how these equations can capture both the exponential and the more complex growth patterns in nature.
So what was that? Can you give example of the differential equation when solved, give exponential solution and basically how that exponential solution help us to understand the kind of problem we had.
Absolutely. A classic example is the simple exponential growth equation, which is often written as the derivative of the population with respect to time equals the growth rate times the population. When we solve this, we get an exponential solution, meaning the population grows at a constant rate over time. And the solution looks like the population at any time is the initial population times the exponential of the growth rate multiplied by time. This exponential solution helps us understand that in the absence of limiting factors, the population will grow indefinitely at that constant rate. It's particularly useful in modeling situations like bacteria growth in a nutrient rich environment or certain financial models where growth is compounded. It really shows how, under ideal conditions, growth can be rapid and unbounded.
Can you give example from the human body where we can see observe the actual change and we can predict its solution by this differential equation?
Absolutely. One great example in the human body is how we model the rate at which a drug is metabolized and eliminated. For instance, in pharmacokinetics, the concentration of a drug in the bloodstream often decreases exponentially over time. This can be modeled by a simple first order differential equation where the rate of change of the drug concentration is proportional to a current concentration. In other words, as time passes, the amount of the drug in the body decreases at a rate proportional to how much is currently there. By solving this differential equation, we can predict how quickly the drug will be cleared from mechanism, which is crucial for determining dosing schedules and understanding the drug's efficacy and safety. It's a great example of how differential equations help us understand complex biological processes.
But that is so complicated. How we can model such a complicated system? Do we know any parameter that we see and observe and wrote down the mathematical term?
Absolutely, it can seem complex, but we break it down step by step. In practice, we rely on measurable parameters. For example, in pharmacokinetics, we might measure the drug concentration at various time points. From that data, we can estimate the elimination rate constant, which is a key parameter. Once we know that, we can plug it into the differential equation and predict how the concentration will decline over time. Similarly, in other biological systems, we identify key measurable parameters like rates of growth, decay, or absorption, and use them to form the mathematical model is really about combining empirical observations with the math, and that way we can make sense of complex dynamics.
Like rates of growth, decay, or absorption. Okay, thank you.
You're very welcome.